Hi everyone, this video will talk about designing a filter to remove noise that corrupt ECG1 signal given. So, from the data given, we use MATLAB to find its frequency spectrum. In order to do that, we find the discrete Fourier transform of the signal and transform it to the Fourier transform and plot the magnitude and phase spectrum. So, here we have the code from the phase 1 where it will load the ECG1 and we define the sampling frequency, the sample size and the time domain, and we plot it using this command. Okay, and in the part of transform it or to obtain the magnitude and phase spectrum, so we use this code from phase 2. So we use the discrete Fourier transform where we use the k domain here, and we transform it to the Fourier transform using the k to f domain equation, and we plot it using this equation, using this code. Okay, 1 minute and 30 seconds.
Now I'm going to explain MATLAB code for filter design. First, we initialize the filter order equal 58, and by using the for loop to vary the filter order from 58 until 158. Then we using the FIR1 function to do the FIR design using a window method. The input is filter order, frequency constraint, and also the filter type. The filter order is varied from 58 until 158 mentioned before, and the frequency constraint is equal cutoff frequency divided by sampling frequency, which result 40 divided by 500, and 40 is because the noise frequency is at 50, so we put 40 Hertz as the cutoff frequency, and the filter is low pass filter. And then we use filter function to apply the filter to the input ECG1 signal and generate the output filter data. To check whether our filter data is successfully remove the noise, we are plotting the frequency spectrum of the filter data. Then after loop to find the filter order which is enough to filter the noise, we are plotting the frequency of the frequency spectrum of the filter, and also the graph of original ECG1 signal and low pass filter ECG1 signal to do comparison. And the frequency spectrum of the filter data, low pass filter ECG signal is plotted as highlighted here.
As for my part, I am going to explain about the outcome of the whole coding. Figure 1 shows the ECG signal 1, which is sampled at 1000 Hz. As we can see, the signal is distorted due to the 50 Hz power line interference. Figure 2 shows the frequency response of ECG signal 1. From the magnitude response, we can see this extra signal component at 50 Hz, which is caused by the power line interference. Figure 3 shows 6 different frequency spectrum of low pass filtered ECG signal 1 at different orders, which is at 58, 78, 98, 118, 138 and 158. From this we can see that as the order of the filter increases, the magnitude of the extra signal component decreases, and finally when the order is under 58, the signal is there is no extra signal component at the 50 Hz. Figure 4 shows the frequency response of low-pass filter at the order of 158. It is clear that this low-pass filter is designed using Hamming windowing technique. Finally, Figure 6 shows frequency spectrum of low-pass filtered ECG signal 1 when the order is 158. From the magnitude response, we can conclude that the signal is totally noise-free.